Stepping right through the textbook, we're now at 4.10.2, norms and condition number. Norms are a measure of the magnitude of a matrix. There are several different ways of measuring that norm. In fact, we're going to start here with these three examples of the magnitude of a vector. So you have the infinity norm, the I norm, and the Euclidean norm. You've probably been taking the Euclidean norm in other classes or other scenarios without even really knowing it, but the infinity and the I norm are also important to understand. So the infinity norm is pretty easy. We're dealing with just a vector, so it's one row or one column. The infinity norm says you take the maximum sized element, and that is the norm. So the maximum absolute value, whether it's a negative magnitude or a positive magnitude of any individual element in the array, becomes the norm of the matrix. So you just look for the biggest. It's identical to the max function. Maybe max if you're finding the absolute value. The I norm. This is whenever you take the absolute value of each element and sum them together. So every element of the array makes a contribution. You take the absolute value of them all, sum them up into one big number, and that measures the absolute value of all the elements in the row. The I norm of all the values in the row. And lastly, the Euclidean norm is the one that has some physical realization because it is the square root of the sum of the squares. The Euclidean norm for a 3-vector array, as described here, is the magnitude of that 3-vector array. For two dimensions, it's still the length of that vector. So this one has a physical realized quantity where you sum up the squares of each individual dimension, take the square root of the whole thing, and get the magnitude of the vector itself. That's probably the closest to reality these settings of these different parameters will come. So the thing that bothers me about this is when someone says go take the norm of a matrix, which one are they referring to? They might specify, take the infinity norm, or take the I norm, or take the Euclidean norm. But if there's so many different flavors, how can one be right? They certainly produce different answers. So it seems a little bit non-mathematical to have multiple options for the same type of goal. Now, expanding this out to 2 dimensions, things change a little bit. So you, again, have the infinity norm, the I norm, and you also have a 2 norm. But complications arise. So you still here take the absolute value of the ij element, and you sum them up across all of the different rows. So you sum up an entire row, and you look for the maximum value of the summation of absolute values in any row. So if you have 10 rows, for each one of the 10, you'll take the absolute value of every element, add them up. So row 1 would have a total value of A1, row 2 would have a total value of A2, etc. You go all the way down the list. And then the row that has the largest maximum becomes the infinity norm of the entire matrix. So that sounds interesting, but when we look at the I norm, it looks to be virtually the same. Summation across a row, absolute value of ij. Then look, maximum from 1, or j is less than n is greater than 1. I believe your textbook meant to put the summation from I equals 1 to n. That would make more sense because then you're adding the summation of the absolute values of each column and scanning from the left to the right of the matrix to find the I norm. If you read the description, that seems to agree with my description of perhaps another small typo in the text. And lastly, the 2 norm of a matrix is more complex because the new terms here are actually eigenvectors. So for as finicky as these norms are, I would encourage you at this point until we find a more justified use of calculating such a complex norm as the 2 norm, use MATLAB's built-in function for that. There's one that's built in. I believe it's norm, parentheses, matrix name, comma, 2. Of course, the Euclidean norm does exist for a matrix as well. You have to do a bidirectional summation. So basically summing up every single element of the matrix. So A of ij of every location is squared and added together. And then once you take this total summation of every element squared, you take the square root of that whole mess and you obtain the Euclidean norm of that entire matrix. So the norms will come up in our further discussions of eigenvalues, eigenvectors, and how to find those numerically. But they can also be used a little bit to determine the convergence of a matrix, whether the matrix is well conditioned or not. One last connection before we get too far ahead, since it's right here in the book, we'll discuss it. That the error of a matrix, if you know the error and you know the inverse of the coefficient matrix, then you know residual. If you know residual in the inverse, then you know error. You can travel back and forth between these two quantities. Residual and error are directly related if you have knowledge of the inverse. If you don't have an inverse matrix, if it becomes singular or something, well, you have neither error nor residual because you can't solve your problem. So, having gone through all the norms and discussions of the different methods that can come up with that, what do we do with it? One thing that can be done, whenever you see these double vertical bars, that means norm, you can take the norm of a coefficient matrix, multiplied by the norm of its inverse, and that product becomes a condition number. So the only matrix that would have a condition number of exactly 1 would be the identity matrix. The higher the number gets, the farther away from 1, the more poorly conditioned the matrix is. But what's interesting is, like, how high is too high? Which norm definition do you use? It's all a little bit obfuscated, in my opinion. Which is unfortunate I have to use the word opinion when referring to mathematics. So, the value of the condition number depends on the matrix norm that is used. That is a problem, because if we use a different method, we get a different number. But again, they're all just relative signs without completing a entire mathematical process that's relatively involved, as I'm sure you've seen in several examples, that tells you whether or not the system is highly, highly sensitive. This deals directly with the discussion of ill-conditioned systems. This example is a perfect example of an ill-conditioned system where if you take, perhaps this is a system of equations representing a suspension or something a simple second-order system of equations. If 3.85 is correct, then the system solves to an answer of x1 equals 45, x2 equals 130. If you measured that, perhaps we call it a spring coefficient. If the spring coefficient was actually 3.84 instead of 3.85, and you resolve the set of equations, you actually start getting x1 equals 110, x2 equals 325. So a massively different solution just from a tiny, tiny little change in the overall coefficient. And this can be predicted by looking at their conditioning. The condition of matrix A, the coefficient matrix in question of the problem we just solved. So norm of A times the norm of the inverse of A. If we used the infinity norm, we get this first option. So the infinity norm of A is 15.35. The infinity norm of the A inverse is 175. That gives us a product of 2,686.25. If we took the I norm, same answer. 2 norm, different answer. We could take the Euclidean norm, be even more different. The thing is, they're very far away from 1, telling you that this system of equations is nearly singular. It is poorly conditioned. So small changes in your plant matrix, small changes in the coefficients can produce very, very large changes in the output. So you should be careful in solving systems like this, or perhaps seek a representation of the equations if you have alternatives. Or perhaps you even go as far back to changing the mechanism. Maybe this shows you that your mechanism on the design, whatever spawned those equations to begin with, is far too sensitive, is far too stiff, is far too something that makes the solution variable. This is where everything works in MATLAB, everything works with numerical perfection, but once you start going to build something, if you do accidentally put a chip in a structural component, or if you change a spring constant by a small amount, that could change the entire plant matrix. If you're dealing with a poorly conditioned system, an ill-conditioned control system perhaps, then everything else can break down around it. So that is a good discussion of norms and how they can be used to find a condition number, which goes on to describe the behaviors of ill-conditioned systems. Again, in all of this, if you have a singular matrix where the determinant is 0 or the inverse is undefined, you don't have to worry about condition numbers because you can't solve it anyway. So that is the ultimate in failed solutions. This just tells you if your solution is dangerously sensitive to numeric noise and numeric offsets, which can arise in several modern systems.